Okay, hey everybody. Today my group is going to present on an asynchronous distributed mini-batch Frank-Wolf optimization algorithm. So, Frank-Wolf algorithms, also known as conditional gradient algorithms, are first-order iterative methods for solving constrained convex optimization problems. They've recently received a great deal of attention in a lot of machine learning communities for a few reasons, namely structural reasons. They often are good at providing sparse and low-rank solutions, for example. They're often simpler than other constrained optimization methods. For example, they're often simpler than proximal gradient methods, which is another common method for solving constrained convex optimization. And really importantly, this simple method allows for scalability with big data because you're doing a very simple kind of step as a subroutine. And this allows you to scale it up to big data a lot better. So just going through the classic Frank-Wolf algorithm that we hope to parallelize. So you start by initializing a point, x naught. Then for each iteration, you just basically solve a linear program here. So what you're doing is you're linearizing your objective at your current point. So you're forming a tangent hyperplane at the current point. You solve this linear program. And then your iteration is you're just making a step towards the solution. So you actually interpolate between your current point and the solution of this linear program. Whereas iterations increases, you move less and less towards the solution of the linear program. And this is the entire algorithm here. So in this project, we have two main goals when we develop this asynchronous distributed mini-batch Frank-Wolf algorithm. So the first goal is that we want data points to be distributed over multiple machines, where each machine performs stochastic gradient updates. So that's the mini-batch part. And second of all, we want each machine to send updates to a central server in an asynchronous parallel manner, i.e., where we don't wait for other machines to complete iterations before continuing. So in this presentation, we'll first of all provide some background information about some existing methods that we extend in order to develop our parallel algorithm. We'll describe our asynchronous distributed mini-batch Frank-Wolf algorithm. We'll explain some system design, how we carry out these two objectives that we've laid out, show theoretical guarantees, and then some preliminary empirical results that we have.
Hello. Hello? Can you hear me? Okay, sorry. Okay, so this is the work which our work is based on. This is the 2013 paper by Martin Jaggi and co. So the left-hand side shows the classic Frank-Wolf algorithm, and the right-hand side shows the block coordinate Frank-Wolf algorithm in Martin Jaggi's paper. So the constraint space M is assumed to be block separable. So there are n blocks, and Mi corresponds to the ith block constraint space. And this minimization problem can be broken down into n subproblems. Okay, so that is what we are doing here. Si equals min Si and gradient in the ith component, ith block actually. And this block coordinate Frank-Wolf algorithm is like a randomized method where you pick one of the n blocks and solve that subproblem, and you continue doing that. So our method is sort of based on that, where instead of picking just one subproblem, we solve tau subproblems, and we do that by distributing the tau subproblems to worker machines. So this can be done simply in a synchronous manner, but we do it in an asynchronous manner to gain more speed. So this describes one iteration of our method, the asynchronous method. So the server guy has the current iterate xk and the gradient, full gradient at the current iterate. It broadcasts it to all the workers, and then the workers keep sampling for the subproblems, and then they do their work and then send it back to the server and put this triple consisting of the block number, the iterate number, and the subproblem solution to a queue. They put it in a queue, and the server reads the queue and then forms the next solution basically. So we have to note that the workers do not communicate with each other. So while sampling the subproblems, they can two workers can solve the same subproblem. So there is some sort of redundancy, but the thing is, even though there is redundancy, because the workers do not have to work in a synchronous manner, it can be faster. There can be faster worker nodes and slower worker nodes. So this method is going to give an advantage in that situation. So how bad is that redundancy? Like we say that if you want to solve, say, tau subproblems, the total number of work done, that is T subproblems, is bounded. With high probability that the number of total subproblems solved is less than or equal to twice the unique number of subproblems that need to be solved. So in summary, even though there is redundancy, it is not too bad. That's what I want to say. Yeah.
Okay, so I want to talk about some of the system implementation. The preface is that we haven't actually implemented in distributed setting. We only tested on MATLAB simulation. But here are just some of the directions that we want to go down the road. One thing you notice is that for this thing to work, you have to distribute both the data and also distribute both the parameter and then also do some scheduling at a central place. So if you have a traditional parameter server, you might have heard of parameter server where you kind of have just this distributed shared memory abstraction, right? That would not work because it doesn't do scheduling per se. So what we need in addition to the parameter server is that the parameter server has to understand, okay, it has to collect enough coordinates for this epoch, and after that, tell every worker that, okay, you can move on to the next epoch, right? Because in each epoch you compute enough coordinate, you minimize according to along a few coordinates, and then actually tau coordinates in the previous notation, right? So does it say? So here, yeah. So you need to collect enough minimization updates, actually tau of them, in order to move on to the next epoch, right? So what we can do is that, okay, you can let each worker have a partition of the data, and then they compute the gradients, send to the server. The server collect the gradients, send to the workers, and the workers starts randomly pick their coordinates to minimize over, and then send the updates to the server, and then the server, once it collects enough updates, it will tell the workers to move on, right? And then also send the new gradients to the server, to the workers. And also, one thing you need to note is that we want enough parallelism. We want the tau to be large enough so that each worker has enough work to do, so that the computation time will not be dominated by communication, right? Because if you do a distributed setting, communication is actually very expensive. So you don't want each worker, you don't want the subproblem time, solving time is too short compared with the communication time. So that could vary from problem to problem, right? Because some problem has more complicated subproblem, and then so you can tolerate smaller parallelism, and then so essentially each worker can just solve just one subproblem. It takes a long time, right? in that case, you can choose a smaller tau, but sometimes if you have simple subproblem, then you have to have large tau so that each worker solve more subproblems and takes more computation time. And also we can do something more clever, essentially just you can duplicate the data, right? So suppose there's straggler, then the other workers can help out because you just randomly pick the coordinates to optimize. So whichever worker picked those coordinates doesn't really matter. And that's the beauty of doing this synchronously. And then I just want to talk about a little bit the specific application problem we're solving. It's the structure SVM. And then the problem formulation is just is similar to the dual of regular SVM, except in this problem, the alpha vector is actually very high dimensional, right? So suppose you look at OCR application where you have a bunch of patches, and then you want to recognize what letters are those, right? So you want this latent state to tell you which letter out of 26 letters are the correct one, right? Are the true one. So your space, your latent space is actually exponentially large, and then therefore your alpha vector in this case will be exponentially large, but it's very sparse. So we want to solve this problem by using Frank-Wolf, which preserves the sparsity, and then the subproblem for this particular structure SVM turned out to be simple, and that's how we can exploit the Frank-Wolf algorithm. So I'll hand over to Yuxiang.
Okay, thanks, Daiwei, for talking about the system components of this project. As Daiwei mentioned that we, for better asynchronous properties, we might want to choose tau to be as large as possible. But everything comes at a cost. So as we will see in the convergence analysis, that we couldn't actually choose tau to be too large. And that is also reflected in the experiments. So this is our convergence analysis. And we show that in these two results, that both objective function value of the primal objective and the duality gap in expectation converges at the rate of roughly 1 over k. But as we may notice, there is a pretty disturbing dependence on n square on the top of the equation, and n is a number of data points. So this is very undesirable. By the way, this convergence result actually contains the block coordinate Frank-Wolf's convergence result and the batch Frank-Wolf special cases if we choose tau to be n for the batch method, and we choose tau equals to 1 for the block coordinate method. And this is a simplified version of our convergence result, and we have the variance for approximate oracle solves and other things. But like I said, it all boils down to how large is this constant CF tau. I haven't told you anything about CF tau, but that's the actual critical part of it. If CF tau is small, if it is as small as 1 over n squared, then this thing converges extremely fast. But that doesn't seem to be the case in our analysis. So what is the curvature tau in the first place? So it is very similar to the gradient Lipschitz constant, but it is slightly stronger. So we require that for any x and any x plus delta s that is in the domain, where delta s is the restricted updates only towards a subset of the coordinates, which is only a size tau subset of s within 1 to n coordinate blocks. And we require that this update, regardless of which x and which update step and which gamma between 0 and 1 we choose, is always lower bounded by some gamma square times curvature constant over 2. So this is a key definition in almost all the Frank-Wolf proofs. And yeah, we require this constant to hold for any x delta s and gamma. And our definition of CF tau is the expectation of CFS if we choose this subset randomly from S as a subset of 1 to n. So it can be shown that this is upper bounded by the Lipschitz constant corresponding to this coordinate block times the diameter square of the space we are optimizing over, projected only on the coordinate. So it can be shown as in the original block coordinate Frank-Wolf paper that the worst case upper bound of this CF tau is pretty bad. Basically, it scales the same as tau square over n square. And if we plug this back into our convergence rate, we can see that the tau canceled out. And we end up with the same convergence rate regardless of tau. This is very disturbing. This means that if we increase the number of machines and increase the size of the mini batch, it doesn't actually improve the rate of convergence, theoretically, in the worst case. So we can choose tau equals to 1 and optimize over 1 coordinate, and we can also choose tau to be as large as n and do the batch update, and the rate of convergence are going to be very similar. So this is the most disturbing part of the project that we have been having trouble dealing with. But, well, it's basically a negative result.
So
Yeah.
it's very interesting that you do not analyze the correlation between the coordinates. And does this have to do something with that?
Yeah. In the current situation, we assume the constraints are on the product domain. So each block of the parameter we are optimizing over has its own constraint that is unrelated to others. But they are correlated in the objective functions that we are minimizing. So that comes in the very beginning of the talk. So we have been trying to answer these open questions. So besides the structural SVM, are there any problems that the worst case convergence rate actually depends on tau, and in particular, it's faster with increasing tau. And if this is the case, this justifies our distributing the data and the system so that it gets faster convergence rate. And on the other hand, we have been trying to work on the average case analysis for the Frank-Wolf applying on the structural SVM. And some of the preliminary results shows that if we assume some underlying model for the data generation, we can actually get faster rate, meaning that the curvature constant can be upper bounded by something that has better dependence on tau. So, as Subrit often mentioned in class, the theoretical analysis doesn't necessarily reflect the reality when you run this thing on the computer. And that's why we conduct the following experiment to test the dependence on tau and scan it between between 1 to something that is slightly larger, and see how much speed up can we get by doing this. And here are the results. On the left, we can see that if we run this OCR data with n equals to 600 something, that again, this is structural SVM. And we can see that the block coordinate Frank-Wolf is here. And if we increase tau, it looks like linear speed up at the very beginning before tau gets very larger, but it flattens out very quickly after tau reaches somewhere like 20 or 30. But this is still very good. Suppose we are running the algorithm on a 20-core workstation, and this basically says that if we do the parallel version of the algorithm, our proposal, we can get like more than 10 times speed up over the vanilla block coordinate based Frank-Wolf algorithm. And we tried something else too. We increased the size of the data 10 times, and it turns out that the pattern is similar. Although we don't get as much like boost when tau equals to 10 or something, because the speed up is only 4, the asymptotic type of behavior seems promising because it doesn't even like flattens out when it reaches like 300. So this gives us a reason to continue investigate this curious issue and see whether we can find something more interesting and to justify that theoretically. So this is basically our project, and I hope you enjoy the presentation. Yeah.
What kind of assumptions did you use for your data generation?
We assume that the feature vectors are joined from a Gaussian random matrix, and basically there's a bokeh and noise model. We used that, but we have no idea whether that's intuitive or making sense in practice. But since that's applied to labeling problem or multi-class classification problem, I think it's reasonable to assume that. Yeah.
So,
basically a mixture of Gaussian type of thing.
so if you run like a Frank-Wolf on the dual, it's almost like equivalent to.
Yeah, we are running the Frank-Wolf on the dual.
Yeah, I'm saying it's equivalent to running cutting pin on the primer.
Uh-huh.
And can you comment on the asynchronous nature?
Yeah, there's a comparison between the cutting plane algorithm and the Frank-Wolf algorithm in the original Lacoste-Julien paper. So I think you might wish to look at that. I haven't like myself understand what is a cutting plane algorithm in the primal.
It's really slow in that experiment.
In the experiment, it's I think it's similar to the vanilla version of BC block coordinate Frank-Wolf, but it's slower than the line search version, and it's also slower than the weighted average version of Frank-Wolf. All our experiments are run based on the slowest version of the Frank-Wolf. That is, we use the fixed step size.
So does the convergence rate depend on the number of machines?
The convergence rate doesn't depend on the number of machines in the worst case, but we conjecture that it is faster with tau being larger than 1, but tau can never be as large as n. Yeah, because the experiment shows that when tau is n, it is very, very slow.
What is n? N is the
Number of data points.
So you
So never do full gradient. Yeah, always do stochastic gradient type of thing. Yeah. So
So this is a MATLAB simulation, right?
yeah,
Does it actually also simulate the communication complexity?
No.
Just calculate it from it?
yeah. This is only based on iteration complexity.
This is your self-coded.
Yeah. Okay. I think we should go to the next group.